Hello, everyone, and welcome back for the final talk of Hope 2020. Before we jump into the talk, we want to again thank you all, attendees, presenters, and volunteers. Your commitment to hope and to our community have made this event possible even in these difficult and trying times. So next up is Charlie Meyers. Charlie's worked on autonomous vehicles and has begun a PhD program in Sweden that focuses on the intersections of computer security, embedded devices, and machine learning. His talk today is titled Borders and Biometrics, Boundaries of Computer Vision, and we'll discuss how machine learning, in particular facial recognition technology, has been rapidly adopted and deployed by law enforcement as a way to justify sentencing, policing focus, and border control. We'll have a QA session with Charlie after his talk, so be sure to submit your questions via the Matrix chat window. Now, over to you, Charlie. Take it away, ground control.
I hope you're enjoying Hope 2020, and I'm simply Mathematics, my GitHub handle at least, and this talk is From Borders to Biometrics, the Boundaries of Surveillance. So a little bit about me. I have a Bachelor's of Science in Applied Mathematics and a Master's of Science in Data Science, both from CUNY. I founded a nonprofit in New York City that provides free Wi-Fi and built a Supernode and wrote some firmware for it. And then I worked on self-driving vehicles at Volkswagen on the verification and validation team. And now I investigate adversarial attacks on machine learning as part of my PhD in Sweden. So my research interests include machine learning and machine learning security, especially in the context of data privacy and anonymization. And machine learning is a huge field. I'm less interested in building new models and more interested in verifying ones that are already deployed and making sure that they can handle outliers and that, for example, a self-driving car system trained in Germany will work in other places around the world, whether due to difficulties in predicting different weather or different pedestrian patterns or just detecting people differently based on the color of their skin. And this hasn't been so much of a problem yet, but in the future, adversarial attacks on machine learning systems will be cheap and widely available. And so we need to prove that our machine learning models are capable of ignoring these or defending against them. And a lot of this comes down to distributed and or parallel processing because we have to do a lot of things very quickly in machine learning. That's the whole point, to deal with gigabytes or terabytes or petabytes of data. And in particular for this field, it's important because you end up doing a lot of subset analysis or a lot of like model optimization in ways that can be totally parallelized. So you can either throw more cores at it or throw more time at it, and usually processors are cheaper. And so, but going into this, there's an upper limit to the number of cores you can have, and so for certain models and certain applications, it has to be done in a distributed fashion. And so collectively, this is called trustworthy machine learning. It's a growing kind of new field. It's pretty interesting. Check it out. And so in this talk, you should expect a brief crash course on machine learning, a brief history of facial recognition systems, a survey of machine learning-based surveillance systems, and fun ways to break them. So what is AI? Well, it's kind of a hard question to answer. These terms don't mean a whole lot and encompass a lot of statistical and probabilistic ideas that wouldn't be totally foreign to anyone taking undergraduate math courses, like linear algebra or calculus. And they're deterministic, so they're like mathematical machines. You put some numbers in, you get a result, and it can be replicated over and over. So it's inaccurate to say that we don't have an idea how machine learning or particular neural networks work. It's just that the decision steps they take are not the decision steps we take, and we have to do extra work to make their decision steps interpretable. And really, this is a weakness rather than a magic feature. It's, we think of it as like emergent intelligence, but as we'll see today, it's just as much emergent stupidity. So machine learning pipelines, as they're called, are made up of a bunch of interlocking software components where you have some data that is fed into like a model that's fit to it. There may or may not be like new user input in the case of like a recommender system from Spotify or Amazon or Google. You need that user input. And then there's some kind of output. Since we're looking at facial recognition systems, it will, you'll see person A, person B as the choice on all of these diagrams. And a little note here is that you can only train your facial recognition systems on an explicit set of people. If I train a model to pick people out of the Senate, it will not make any sense to apply that model to people in the House of Representatives. So that's not necessarily obvious to a lot of people, but the boundaries of your model are defined explicitly by the boundaries of your data set. And for these classification problems, there's not really any work that's gone into exploring beyond explicit classification. The problem is there's a bunch of ways to attack it, these systems. You can poison it. You can evade detection. And you can attack the model itself and get access to its parameters, called model inversion attack. Or you can look at the output from a bunch of model queries, maybe by using their paid service or similar, or using a proxy model you built yourself. You can reproduce the original data, which is terrifying in the context of facial recognition systems, because that means that a particularly motivated attacker could find all of the individuals that comprise the original data set. So there are a couple ways to divide machine learning systems, and they fall into like regression or classification category, where regression is like this. You may be familiar with Excel, where you have a bunch of data and you're trying to draw a line. That in this case, this might be housing prices, and you have a bunch of other variables that go in to determine that, and you fit your line to it. And then there are classification problems where you're less trying to find a function that approximates the collection of your data, but you try to find a function that separates your data. As you can see here, these are a bunch of different ways to do that. Additionally, this is a supervised system in that your housing prices are a known value, the Y value, and your other variables are also known, X. And so you can evaluate the error explicitly. Now, these are unsupervised systems. The orange and blue data are there for us to see how these things clustered them, but there is to say like no correct answer here. And because this is unsupervised, these don't have inside and outside labels. And so you have to come up with other techniques to build some kind of confidence in the results. So facial recognition systems have been around for decades, since the 60s. Some of the earliest systems on computers were built for facial recognition systems, precisely because of the military applications. So because of the military applications, it was very important to get this done. And it originated by laboriously measuring people's faces, like the width of their nose or the distance between their eyes, and creating a data sheet for each person, which would stand up pretty well to like any problems with scaling or rotation or aging. And so, but it was very laborious and it took a long time to do these measurements. So you needed kind of a captive audience of volunteers to get the faces from. And so Microsoft, IBM, and the US Army created internal databases of this that were massive in the 90s so that they can move beyond these small scale tests popular within like a small university computer science department. One of these data sets became the ferret data set, which has been widely cited and widely used. Now models rely on 3D face scans, images, or videos and have upwards of 99.999% accuracy for some groups of people. However, there are problems with gender and racial disparity. And MIT researcher Joy Buolamwini, I hope I'm not butchering her name, and the current George Floyd street protests have brought this technology into the spotlight, and several vendors have withdrawn them from the market, including Microsoft and IBM. Historically, there have been different detection methods. There are like matrix decomposition techniques that work well on other types of signal data, like for example, one technique is very good for isolating sound in a noisy room. The math does not work out very well for facial detection systems. It peaks around 80% accuracy. Landmark-based detections do better because they're robust to scaling and aging and small facial feature changes. And then there's correlation searches, which work on like average faces, looking at like a sum of average faces for that define a face, or averaging each class so that each class has a kind of like meta prototypical face, and comparing these to some input face. But these are also like matrix decomposition algorithms beaten by glasses, facial hair, aging, head rotation, and any minor variation in the person's face. And so neural networks overcome all of these and can figure out their own features, like the location of the nose, by themselves. But they do this at the cost to security. So here's an example of the like matrix decomposition faces. These are called eigenfaces, where essentially you have a collection of independent. These are not in individuals' faces, but these are kind of prototypical faces that can be used to distinguish individual faces. And the math of this is maybe like ends up being like 4 or 5 lines of code, versus modern systems where you have these massive neural networks that have a bunch of convolutional layers that pass these cascading filters across and compression, and then you repeat this process several times, and then at the end you get an output of probabilities, and then you find the one that has the highest, and you say that's the face you think it is, and it's this like very strange mathematical machine that's can have many millions or billions or hundreds of billions of parameters. But, in between those decomposition systems and neural networks, there was the Viola-Jones algorithm. And what it does is it turns it turns an image into a set of geometric features, and it quickly rejects images that don't have certain features. And so, and the way it does that is by looking at an image through these filters. So it will take some raw image data in black and white, and it'll pass it through, it will multiply it against another matrix, which in this case, in the case of A, would be zeros on the left-hand side and 255 on the right-hand side for a 3-bit image or 3-byte image. And what that does is it essentially looks for a long vertical line, and then the B will look for a short horizontal line, the C will look for a short vertical line, and the D will look for a diagonal. And the algorithm picks these filters in such a way that is designed to quickly reject things that are not faces, because it has to do this kind of filtering and across many different orders of scale. This algorithm works on an image with a single face as well as images of a crowd of people. So the problem is that a lot of the research in the 90s was based on these groups that do not reflect the human population. They were overwhelmingly white and male, as we can see from this chart. I took kind of more typical data sets, the ferret developed by the Army in the 90s, and the labeled faceless in the wild data set, which is a collection of the most famous celebrities. So overwhelmingly Hollywood actors and disproportionately American and white. And then there's Fairface, which is a data set that was intentionally created to be as close as possible to an actual human random sample. So as we can see that when we look at the luminance value of the people in these images, or at least the foreground, we find that you have almost a bimodal distribution for the ferret database, which is the smallest one down here. And so it's not very good. We would expect this to be normally distributed. Then for the LFW data set, it is normally distributed. And it looks fine until we realize that both of these data sets are significantly lighter than what we would expect from a data set built from randomly from the people on the planet. And so what this means exactly is that these detection systems that are used to inform, where faces are in the animation, then get used as part of the data collection process, as part of the training process, and as part of this cyclical kind of spiral of things being ignored. And it's not so bad, because as we can see, things are generally detected. The ferret data set performs the worst here because it includes profile pictures, as in people turning to the left or right or at 45-degree angles. And there are different Viola-Jones detectors trained specifically on those angles. And this one was trained just specifically for frontal. So this verifies that this does not work very well on rotational changes. But what we see here is that the open face detector performs much better on the celebrity data set than it does on the real population data set. And perhaps that's due to problems in the training stage. I don't really know, because the open face system is proprietary, or at least the data they use to train it on is proprietary, or not released. I don't know if anyone actually has business interest in it. And we can see that this carries out in the racial performance. And in Fairface, when we look at different racial groups of people, we find that the difference between the smallest and largest gap is around 1%, which is totally fine. That would be definitely in the range of statistical randomness. But that is not true for the like 8.5% and 11% we see in Fair and LFW. So we see that when we use these bias detectors to build facial recognition systems or facial recognition data sets that become those systems, we have this cascading problem where 10% of the people who are where it's 99% accurate for white males and 89 to 85% accurate for minority groups. And so I started looking into why this would be happening. And I looked into OpenFace and OpenTV, which are two big libraries for doing this kind of facial recognition system. And I found in their source code that deep down that they're both installing DLib. They're both installing DLib, which is a library developed in the 90s that uses this Viola-Jones detection algorithm trained on the overwhelmingly white data set. And what we see here is precisely that when we have when we train it on these overwhelmingly white data sets, our performance goes way down. So this is the DLib detector versus the neural network based one in OpenFace. And we see in the best case, our detection system is about as good as a coin flip. And in the worst case, it only detects 10% of the faces. And, that was really abstract and kind of like hard to like conceptualize. But so I found this Verge report from about this algorithm called Pulse, which depixelates images. And I looked into Pulse and found what it was using as its base detector in the generative adversarial network it was using to create the novel images. And it turns out it was using DLib. And so DLib is taking this pixelated picture of Obama on the left, and because of the way it is encoded white and maleness, it produces the images on the right. So there's a saying in machine learning that is always, always, always true: garbage in, garbage out. The data used to train these systems is very, very important. So this is part of the Fairface study, and they evaluated several different data sets for the racial composition. And so here's what it is. So one of the ways that our models become inaccurate is through bias that we didn't intend to include. And it's bias that comes from larger systems in society, in data collection methods, in what kinds of things get funding, and et cetera. And then there's intentional attacks, which we have discussed a bit. And the famous example is having a few pieces of tape on a stop sign will make this an autonomous vehicle think this is a speed limit sign, which could have disastrous consequences. And so, as I said a little bit before, there's 4 different types of attacks. Poisoning, where you inject data into the training process so that you can manipulate the model. And then there's evasion, where you're trying to get the model to misclassify some data. Either you want it to, for example, misclassify your spam as ham, or misclassify your botnet as a legitimate user. And then there's data extraction, where you or extraction attacks, where you extract the model itself and create a copy of it through examining enough of the input-output pairs. And then you can actually create a copy of the input data by doing the same thing. So we've got poisoning and evasion. So poisoning attacks the model, and evasion attacks the user input. And they're essentially the same, but mathematically speaking, or conceptually speaking, they just happen at different points in the process, like whether it happens before or after training. But the general idea is that you have some kind of like class boundary. And with poisoning, you introduce a new data point that shifts this class boundary such that things are misclassified. And with evasion, you do this in such a way that your malicious attack falls on the other side of the line here. And so they're essentially the same, and they are rooted in this like geometric interpretation of the data. And here, we have these 2-dimensional data sets, and where this gets tricky is we have when we have very large data sets that might have like tens or hundreds of dimensions. So like your average megapixel image has 1 million dimensions because each pixel becomes its own independent vector. And so, it becomes impossible to like represent images in this way. And so what this means is tiny numerical coincidences can sum up in such a way across this million vectors that we can have things very confidently misclassified by detection systems. And as you can see, you add an imperceptible amount of noise to this image of a panda, and you can convince the computer that it is a gibbon. And in fact, it is more confident this adversarial gibbon exists than it was that this benign panda existed in the beginning. And then there's inversion attacks, which look at the output from the model. And so model output these days is from these neural networks, where you have convolutional systems defined by this mathematical formula at the top, where you have 2 sums and 2 functions, f and g, where f is just sliding across the frame that is G. So if G is like a 10 by 10 grid, then F is sliding across that 10 by 10 grid so that every block of cells is evaluated separately and at different scales. And that's what a convolution is, this fancy star symbol. And then neural networks are just like a bunch of those convolutions with some weights. So the convolution is happening in the dots, and then the weights are the lines between the dots, and they add up. And then you have like some input space where you have like image data, and then you have a bunch of convolutional layers, and then you have some kind of like output layer that produces a probability that you can interpret as a classification. Now, I know that was a little hard to understand, but hopefully this image helps. And so what convolution does is you have some like input image G and some function F, and then you get some feature map, and then it keeps doing this kind of like reduction and compression until you end up with just a probability at the end. And so, but the main problem is when we look at all of these systems, they're just kind of simple linear algebra steps. Like you have some additions, you've got some multiplications. I mean, you've got some vector multiplication, but in no case, but none of these functions are really safe or cryptographically safe. That is, they are invertible. And so all you really need is a certain number of observations for a certain number of parameters. Those have to to determine some function that inverses the model itself. And so what we find is that this is now just a linear problem where with linear constraints, and that means that if we have 10 parameters in the model, we only need 10 observations. And certainly this slows us down a little bit on this, in the sense that neural networks can have hundreds of billions of parameters. But I can also train a proxy model that approximates your model fairly accurately with a much smaller number of parameters. So I might only need a few million or, tens of thousands, which in the age of automation and cloud computing is relatively trivial, especially since a lot of these services are set up as paid services. So they wouldn't necessarily see your exploratory attacks as malicious if you're paying them for them. Now, outside of the context of facial recognition systems, these kinds of attacks have huge potential to disrupt like financial markets, because you have high-speed traders competing with each other to move very large chunks of the market very quickly. And if Goldman Sachs knows that Chase is going to move a certain direction, but at the same time Chase does, then they can hedge against that and manipulate the market. And at the same time, if a botnet or a hacker wanted to create a DDoS attack, it would be easy to do this with these techniques, because you could have a just massive distributed system that is constantly probing like Cloudflare or Google to get through their DDoS protections and figure out what parameters do and don't work. And at the same time, this attack also allows for deepfakes, as we'll see. So there's an inference attack, which instead of just exposing the model, exposes the original data. And it works under the same mathematical assumptions that you need as many input-output pairs as were dimensions in the original data. Again, that's a kind of a oversimplified term. You could potentially do this with a small fraction of the number of dimensions. So if this is a 1 megapixel image that's, you know, 1,000,000 dimensions, then you might be able to get away with only 10,000 input output pairs, which sounds like a lot, but isn't in the scale of cloud computing. And so what does that mean? Well, there's widespread use. Facial recognition systems are used by Frontex to track immigrants across Europe, particularly because a lot of people are coming from war-torn places and don't necessarily have identity documents. They're already being used in airports in the US and the EU. In the EU, I ran into one last year that was being used to replace passports in the wake of COVID. I guess that was this year. Wow, that seems like it was a long time ago. So it was being used to replace passports, so no one had to touch anything, and it was running Windows XP, which was a little terrifying. And even recently, they've been used in upstate New York for safety, to make sure that like everyone on campus was supposed to be on campus, and that was very controversial. Additionally, there's been reports that the NYPD has been using Amazon's facial recognition system to find suspects using just composite sketches, which, as you can see, the systems do a good job at matching the sketches, but that humans are failing to accurately represent the people in their memory when the sketch is happening. And so these systems are, you know, with very high confidence matching people, but the people they're matching are not guilty. And this runs against NYPD's internal data that says there were only 5 misidentifications out of what appears to be nearly or slightly more than 10,000 uses of the technology. So there's some disagreement between the press and the NYPD about what's going on, how widespread and how useful these tools are. So I mentioned Joy Buolamwini at the beginning of the talk, but I wanted to bring up her research. And so she did a great job of evaluating commercial systems. And so she, you know, used IBM and the OpenFace and Microsoft and Adient's systems commercially to evaluate them against disparities in gender and skin tone. And as you can see, like males outperform females and lighter people outperform darker people. And this is from 2017. And we find that after her first work was published, things began to change. You can see that the audit produced reduced error across all areas in a year, but particularly for darker female and darker male, which is good because those were not doing well. So that this follow-up research, as you can see, was done in 2018. So in 2020, the EFF sues the Trump administration, calling these a threat to civil liberties and privacy because Americans cannot take precaution against the covert or massive capture of images. San Francisco and Boston banned the use of facial recognition by law enforcement. The EU considered a ban, but stalled amid COVID and some difficulties in dealing with Frontex and Interpol. And this has already been rolled, but however, this has been rolled out in airports in the US and Europe, and the EU ban wouldn't have covered it anyway, since it only was considered for public spaces. And these tools are already used for repression and surveillance in China's Uyghur internment camps. And so this is like actively a huge problem. And so, but what's interesting is they're still very fragile. Like, we went over all the ways to attack them, and all you're really doing is shifting this boundary condition, which no matter where I drive this boundary condition, I can always craft an example that allows me to shift it. Here's a t-shirt. As you can see, all of these other people are detected, but this guy is not even shown up to be a person. This woman is confused to be is thought to be a bunch of license plates because she's overloading the sensors. This breaks the Violet Jones detection algorithm because it undermines essential functions about eyebrows and the bridge of one's nose and how those appear geometrically to a camera. And the Department of Homeland Security is now worried about COVID masks and how they play a role in the George Floyd protests, and how and they're afraid that subversive groups will use the occasion of public face masks to do vandalism and other riotous acts. Which is funny because they sell these anti-surveillance like face masks on Amazon that combine the techniques seen in the t-shirt with the just covering your face. And this is even into the world of high fashion. This is called dazzle makeup. And this designer has come up with different ways to break facial recognition systems. As you can see, they rely on like playing with the geometry and the assumptions and the shadowing in human faces. And then finally, we've got this other system which projects a constantly morphing face onto your own, kind of like a Rorschach mask. And so, you know, these systems are trivial to break. They're very dangerous. They're very accurate, but only under narrow circumstances that are intended by the original researchers. And I hope you know at least a little bit of how to deal with these systems now. And I hope you enjoyed my talk.
So thanks, Charlie. That was a super enlightening talk. So could you tell us a little bit more about how you got into the field of facial recognition?
So I wouldn't necessarily say that's my field. The mathematics is pretty generic and works for all kinds of classification problems. So if you have a different data set, the same tools can be used to differentiate a stop sign from like a speed limit sign, for example. I chose the topic though because it's been in the news a lot recently, and I was particularly inspired by an MIT researcher, Joy Buolamwini. I'm sure I butchered her name, but she had investigated the commercial offerings like G Cloud and AWS and the Microsoft tools for face recognition that we know to be used by law enforcement. And it evaluated their efficacy on rating people based on things like gender and skin tone and race. And since she had established that these algorithms were racist, I was interested in why. And so I took this approach where I looked at a bunch of different data sets to come to show that it wasn't like a function of the models, but it's a function of the data and this like long history of like how these things get built and how these like systemic things influence these models like decades later.
So how many parallels are there between the work you did on autonomous vehicles and what you're doing now? Is it?
So I didn't really do, so I was on the verification and validation team. So my goal, like I would get vehicles more or less from the factory and plus our computer systems. And I would do provisioning and setup and that kind of stuff. And I would make sure, and then I would verify like the continual operations of the systems. But where the idea for the actual paper came up was from a discussion over lunch there, where I was talking to one of the guys from the computer vision team. And I asked him how they were dealing with this racism problem, and if they had come up with some statistical technique, in particular because we were in Germany, which isn't known to be very diverse. How are these things going? How are these cars going to then play out in Dubai or India or New York City, where people look very different? And it became a big company-wide discussion actually around this topic of how do we prevent this from happening to our systems? And I mean, we really didn't have an answer at the time, so I wanted to take some of the first steps. And then I found this PhD program, which was expanding on this idea of how do we trust a model beyond some accuracy? What does it mean for it to be 99% accurate on some test data set relative to the real world? Or and can we find these implicit biases before we try to implement them in models?
So there's some back and forth in the chat, especially about the portion of your presentation talking about masks, the effect of masks in trying to foil facial recognition technology, and elaborate a little bit more on that. In particular, there's a question following onto that about would wearing reflective sunglasses actually work, such as a mirror kind?
So what I found is so in general, for these complex neural network systems in particular, there will always be some adversarial attack you can do. And it might always be slightly different, but there will always be some boundary condition that you can reshape or play, or you can have some boundary condition where you just stay on the line between person, not person. At one point in the talk, I show a woman in a dress with a bunch of license plates, and she still very much looks like a woman, but because there's so many license plates, it spams the math so that the confidence goes towards the license plates rather than humans. And in the same way, masks may be an adversarial attack in the short term against facial recognition systems. There are no shortage of public pictures of people in masks. It wouldn't be hard to take to train a model on a larger set of data and then fine tune it to work with masks. If you only have pictures of say just celebrities in masks, but want to see how this applies to regular people, so DHS is worried about masks being effective in stopping facial recognition. And as far as I'm aware, during the George Floyd protests, the people caught by facial recognition were not wearing masks. But it is trivial from a technological standpoint to make a new system that doesn't care about the masks.
So do you have any suggestions for oversight or auditing of the algorithms and their effects? Any recommendations or any ideas?
So I would defer to to Joy's research on this. In the last couple of years, she's developed an auditing platform available through Media Lab. She works at Media Lab at MIT. I don't have the link handy, but Joy Bulamwini, for people listening out there, and she's a Black woman who is far more equipped to talk about how these things affect her community. And I was just trying to get to some of the more root cause. And I don't know if there's a solution other than open sourcing these models. In another case, there's a model that guides sentencing guidelines called Compass, which is trained on previous arrest data and previous recidivism data, which, knowing what we know about the US justice system, has its historical racism problems. So it's trained on historically racist data. And someone sued Compass, to release this data. And they lost. They were not allowed to see what was making the decision in the model because it was proprietary, even though it was being used by public courts. And so I don't think courts are equipped to handle this. And I'm sure many of you will agree with this if you think of some of the Facebook Congress interview questions and how lost our legislative branch seems to be against the tech sector.
Indeed. Well, we're at time, but thank you so much for the talk, Charlie.
Thank you.
It's really fast and enlightening for all of us, and very important in this particular time that we live in. So on behalf of Hope 2020, all our attendees and presenters and volunteers, thanks for sharing this with us today.
Thank you. Bye.
All right, everyone.